Welcome to Couchbase 102 SDK Operations. In the last webinar, we covered Couchbase Server, understanding the overall architecture of Couchbase, understanding why it's so fast and how it works, how we do consistency and persistence. And in this webinar, we'll be talking more about how to use the SDKs, the operations that are available and fundamental to making your data model. In the next webinar, Couchbase 103, we'll be talking a little bit more specifically about how you use these in creative ways to create a model for your application. And there'll be a number of sample models to help illustrate different ways or techniques or things to think about when you're building a model, and give you some sort of creative fodder to help develop your own model. I'm Jasdeep Jaitla, Technical Evangelist here at Couchbase. You can always email me questions at jasdeep@couchbase.com, or on Twitter you can hail me and do shoutouts at Scalable with the 3 instead of the E there. And let's get started. So one of the first things we do when we get started with Couchbase, after of course we've installed Couchbase Server, is set up the SDK for our preferred language that we're going to be using. So we do support a number of the more popular languages out there, Java, .NET, PHP, Ruby, Python, C, and Node.js. We do have clients for other languages. We call them community clients, although we do participate in the development of some of those clients as well. Because we are an open source company, and therefore we make everything available as open source and also contribute to open source. So for Go and Erlang and Clojure and Tickle and Perl, we have some community clients. And if you go to couchbase.com/communities, on the left nav you'll see an all clients link, and if you scroll down that page you'll see links to GitHub repositories for those community clients. We do have a page, a support page, basically for each SDK, and instructions for setting it up. Basically, if you go to the couchbase.com/communities, it's a portal to all the getting started in, installation, getting started guides for all these languages. One note is for 4 of these libraries, they are actually wrappers around libcouchbase C library. And the C library is extremely performant, and so the wrapper unifies the performance across these clients, which is excellent. But it's important to understand that you need to install libcouchbase first before you install these 4 SDKs. So getting started guide for installing libcouchbase is at couchbase.com/community/c/getting started. A few tips for Mac users. Make sure you have installed Xcode and command line tools. In the new Xcode, I believe that it's actually bundled together and you don't have to do a separate install. But in previous Xcode, before Mavericks, you actually went to your preferences in Xcode and clicked on the Downloads section tab, and then installed the command line tools. Again, for Mac users, install Homebrew if you don't have it already. For Windows users, NuGet is NUGET is a great homebrew-like solution for Windows machines. Make sure you do brew update and brew upgrade and brew doctor to make sure that you're up to date. Again, for Mac users. So installing libcouchbase, the instructions are in communities/c/getting started. However, I'll just give a quick overview. Brew install libcouchbase for Mac. For PC, there's a zip file on that web page that is appropriate for your Windows version and Visual Studio version. For Red Hat, CentOS, and Ubuntu, you get the respective repositories and do the yum install or apt-get install as you might expect. Again, look at the instructions for the C library first before installing the library SDKs for Ruby, PHP, Python, and Node.js. So let's talk about making a connection to Couchbase. So all our SDKs work in a similar fashion. The application server first makes an HTTP request to port 8091 to retrieve the cluster configuration and the cluster partition map. This map, as we talked about in Couchbase 101, contains all the information about the Couchbase cluster, which partitions live on which nodes within your cluster. So the SDKs, the Couchbase SDKs, will keep track of that to make things faster and more scalable, going directly to the node partitions and the IP addresses of the nodes within the cluster that are responsible for those partitions, rather than going through a sort of proxy or some sharding server that will then redirect requests. And our SDKs go directly to the nodes responsible for the partitions. Then after it gets the cluster partition map, it'll establish TCP binary socket connections to each node in the cluster. So in case of one Couchbase server, it'll be just to that one. But if you have 10 nodes, it'll establish persistent connections to each node in the cluster. When you're doing view querying, it'll be done on port 8092. You can do this within your browser as well. You can run queries. Because it is HTTP, you can run queries in your browser. But our SDKs will actually communicate over HTTP to the port 8092 of the servers within your cluster. And finally, there's port 11211. That is the Memcache, standard Memcache socket for backwards compatibility. Our clients actually connect to 11210, but if you use a Memcached client, like if you're doing a migration with your existing application, it will connect to 11211 and use that. Also on port 8091 is the admin console, which if you saw Couchbase 101, that's the console where you can do configuration and monitoring of your Couchbase cluster, as well as add new nodes to the cluster, etc. in a visual interface. So making a connection to Couchbase looks like this. In Ruby, we have Couchbase.connect, and we're passing in the bucket name and the host name. Here we're creating some data. I can do a better zoom here. There we go. Here we've got hash data. We're doing a simple add operation with the key being my data and the value being that hash. Ruby is converting that into JSON automatically, and then I'm outputting the data we get back, and in this case Ruby is actually converting the JSON back into a hash. Python is pretty similar. Here we've got a Couchbase.connect. Here's again a hash, slightly different syntax, but mostly the same. cb.add. So with the connection, I'm doing an add operation, adding my data, and then I'm doing a get on that, getting it back, and then printing it out. So Java is a little bit more verbose. In this case, I'm making a list of URIs, and then I'm creating a client. And in order to make a hash table, I actually have to have a hash table object where I do puts. And so I'm creating the same data here. So in Java, we don't have a built-in JSON transcoder. So in this case, we use Google JSON to transcode that hash table into JSON. And then when we get it back out, it's actually still a string, but we're outputting it with a print line. And if we're doing a serialization of objects here with JSON, and there are a number of different transcoders you can use. I mean, Java has a plethora of different transcoders. JSON's pretty popular, but there's like JSON Smart, and I don't know, there's a dozen others, all claiming to be the fastest, of course. But in the case of object serialization and deserialization, I would want to convert this back into a hash table. In this case, I'm just printing it out. And then for Node.js, JSON is a first-class citizen, so there is no transcoding here. JSON strings are data structures in Node.js, so that's really easy. Here I'm doing an add with the data, and then here's a get, and I'm just logging it out. PHP again, you can see the pattern, creating a new Couchbase instance. Here we're passing in the IP address and the port. and this is the default bucket. Here is an array, which actually is a hash table in this case. PHP is a little interesting. JSON encoding and decoding has been in the default library of PHP, I think, since 5.2. And here we're doing an output of the CB get operation, so add and get. All fairly similar to each other. Each a little bit more, tailored to the language and expectations of how it would work. So operations. Let's talk about operations in Couchbase. These are the ones that you're going to be using when you're creating your data model. The first thing to understand is sort of how Couchbase is organized from a data standpoint. So we do support, obviously, the simple data types like strings and numbers. You don't actually have to store JSON. You can store straight strings and numbers and booleans, and binary data can be stored, and binary data is also a string. So those are all the simple data types, and what you get with JSON is that you can store complex data types, nested complex data types actually. So you can have dictionaries or hashes if you're familiar with more in the Ruby world, Ruby Python world. Java calls them dictionaries, Ruby calls them hashes. And then there's arrays and lists. And now, of course, you can have lists of dictionaries, and you can have hashes with lists and arrays within them. So that's what's beautiful about JSON, is a very lightweight format for encapsulating complex data structures. So JSON is really just a special class of string, and with a specific format for encoding that. This is one of the things that's different about Couchbase over relational databases as well, because you can store these complex data structures within a single document, while if you do complex data types and have to deal with it in a relational without an ORM, you're going to have to normalize that into multiple tables, and even with an ORM, it's multiple tables, and then do joins to get all that back. It's much more involved. Schema is unenforced and it's implicit. What implicit means is that we don't have a schema definition within Couchbase that you must adhere to. Schema can change dynamically, but the reason it's implicit is that it's really encoded in your model layer of your application. Because if you have a user object that stores different fields within the JSON document, that schema is implicit. Data will always have a form. So the form is determined by your application model. What fields are in the JSON, whether there's lists or dictionaries, all that stuff creates an implicit schema. Whether there's optional fields, like address 2, address 3, or a second or third phone number, for instance, may exist for one user, not for the next. So it can vary from document to document, and it can change dynamically. Because the schema is flexible, you don't have to determine that schema ahead of time, but you can dynamically change it with your application, which makes it very agile for development. And it also reduces the initial complexity of starting out an application and developing your model. Often, where you have integrations with, third-party vendors and social logins like Facebook and Twitter, in which case you're getting JSON back from them, and you can simply insert it into Couchbase without having to create a complex schema for their complex data that you retrieve back from Facebook or Twitter or whomever. You're getting this complex data structure, which you don't have to model into normalized tables, each with schemaed rows, and figuring out what all those data types are. Some of the Facebook data that you can get back might take you, days to model the schema for, which is really tedious, and of course that can change at any time. One of the beauties of using JSON in your data store is that it reduces the amount of work that you have to do. So our storage and retrieval operations, we've got get, for retrievals. That's your select, you could say. You have set, which is it stores a document, stores a value, stores a document, and it overwrites it if it exists. This is a sort of a forced write. If it doesn't exist, it's creating it, and if it exists already, it's overwriting it. I typically use add and replace. So add is storing a document but it gives me an error if it exists already. And this helps me with logic. If I don't expect, like a user is doing registration and I don't expect their document to exist, that key should not exist. It should be unique. And if it exists already somewhere, I have maybe a logic flaw. So these exceptions or errors are valuable. So replace is also like, let's say I'm updating user information. If their user key, if that key does not exist for their user document, I have an error, and perhaps that indicates some sort of logic error on my end. So I use add and replace over set 99% of the time. CAS is compare and swap, or check and set is another way of describing it. Basically, it's optimistic concurrency, and you only change the document or replace the value of the document if this unique identifier called a CAS value, which is just a long integer match, and that CAS value represents the current state of that document. Almost like an MD5 hash. It's just a long integer that indicates that the current state of that document. Every time you do a set, add, replace, or touch with expiry operations, you modify the document in any way, it'll change that CAS value to a new random long int. So we also have atomic counter operations. These are always executed in order atomically within a single cluster, just so you understand. If you're using cross data center replication, it's no longer atomic across both clusters if you're doing bidirectional cross data center replication. But within a cluster, atomic counters are atomic, and you can use incr or increase and decr, decrease. Of course, you can increase and decrease by any delta. So these are very useful for key value patterns, very useful for transactional type information like points or some sort of balances, things like that, where you want to execute everything atomically. These are excellent and very unique to Couchbase. Having atomic counters is one of our unique features within Couchbase. Very valuable. We do have a few non-JSON ops. I call them non-JSON because JSON is terminated or encapsulated with braces. So if you use prepend and append, I think most JSON, although it's fine for Couchbase itself, most JSON parsers will ignore everything outside of the enclosing braces. It's not that they're invalid completely. It's that the parsers will ignore them once it finds its final matched brace. But these actually can be used, they're basically obviously used for strings, but you can, prepend and append values within Couchbase itself. So it's actually appending it within Couchbase. You're sending a string with the append operation or prepend operation, and it's joining them together. So you can make quick lists with these. You can, do some interesting things, creative things with these, and I call them non-JSON operations with strings. So this is also available. For those who have used memcached, all these operations should be very familiar. So retrieval operations, if you're doing a get, it's coming out of RAM cache. Right? And this is kind of like a select statement where select star where key equals my key. So you're just getting everything. You're getting the whole document or the whole value. If it's just a single value like a string, or if it's an integer or whatever, or it's a JSON document, you're just getting a select star. You're getting the whole thing. There is no select partial. This is just for your understanding. If you're coming from relational databases, this is sort of like this. Don't confuse the two, because this is not actually a select statement. This is a get, and you're retrieving the entire document. You cannot retrieve parts of documents. We don't do partials. Storage operations for set, like I said before, it'll go to RAM cache. And of course, with all storage operations as covered in Couchbase 101, we have it goes to disk write queue and disk, and replication queue onto replica partition on another Couchbase cluster machine after it goes to the RAM cache. So we stay consistent. Set is like a combination of an insert and update statement in a sense, where the key matches. If it doesn't exist, it's inserting. If it does exist, it's updating. Meaning it always overwrites what's there, even if there's nothing there, or if there's something there, it always overwrites. Add is a special case of set where basically it's more like an insert in that you're setting the key equals value. Also, enters a disk write queue and replication queue after going into cache. And then if it exists already, you get an error. And for replace, very similar. RAM cache first. And that one is more like an update statement. Set the key equals value. Oops. Set the key equals value. Where the key equals my key. And that's just a way of understanding it. If you're coming from a relational world and you need that sort of metaphorical equivalent, that will help. But I think it's best to migrate from that mentality and understand Couchbase as it is. So we've got get for retrieval, and then we have set, add, and replace, and cas. We'll talk about cas in a little bit. So of course, if you do a replace and it doesn't exist, you've got an error. So all right. So consistency. So whenever you do these operations, you're doing a set, add, replace, and even while it's still in the disk write queue, you can still do a get operation. It's consistent. Oops, I'm doing my animations a little too fast here. It's still consistent here. So as soon as you've done that write to RAM cache, if you do an immediate get, it'll read your write. So we are a consistent database. Every time you do an update operation, if you do a get right afterwards, it will always be the new value. We don't have eventual consistency for data. What we do have is called eventual persistence. Eventual persistence means we have these disk write queues so that we can optimize our writing to disk. Disk is the slowest component of any system, even with SSDs. It's still slower than RAM. And so we optimize our performance to use RAM cache first, and then get the latest value. When it gets to the top of the disk write queue, it'll write the latest mutation of that document on disk, and this makes things a lot faster. Traditional databases, relational databases, actually use disk for everything, which is a performance bottleneck, along with other paradigms of having to shard or replicate. Their relational systems traditionally are very, very slow. So this eventual persistence engine, basically gets around the fact that disk is so much slower than RAM. So let's talk about concurrency. So we have optimistic concurrency with cas. So cas is compare and swap or check and set, and every storage operation will create a new cas value, which is just a long integer, which represents sort of like the MD5 hash of that document. So it really just represents the current state of the document. It's like a version number, but it's not a version number, and we don't keep old versions. We don't have multiple versions within Couchbase of a single document. So you can use this cas for optimistic concurrency. The way it works is basically you do a get operation, retrieve the current cas, modify the document in memory in your application, and then do a replace on that document with the new value, and you include the cas number with that operation. And if the cas has been changed in that time by another process, meaning another process has done a replace or a set on that document, the cas will, or even a touch, the cas will have changed, and now you have what's called a cas mismatch, meaning that document is no longer the same version, and so you're going to need to retrieve the new value, redo your mutation, and submit it again with the new cas, or do some other logic which makes sense for your application. That's not always the case where you would want to retry. Maybe in your case you would definitely not want to retry. But this is optimistic concurrency. It requires no locking within Couchbase. It's a simple state management, optimistic concurrency. So application server 1 writes a new document in Couchbase, and we have 2 application servers that retrieve that document. The cas has to be all ones. Now, application server 1 just, modifies that document with the cas and does a get and retrieves the new cas, because now we've modified the document, now it has a new cas. And then application 2 tries to do it, microsecond later, and it's still using the first CAS 11111111, so this is a CAS mismatch, so it fails. And so the logic was, hey, well, let's retrieve it again, redo the mutation on that document, and then use that CAS, and we have a success here. So this is a way of avoiding or dealing with race conditions with optimistic concurrency. Of course, if you retrieve it back, we have a new CAS. Of course, it's not linear. It's a randomly generated CAS. But now they both are in the same state here. So we do have pessimistic concurrency. We can actually do single lock documents. We can lock documents. It's called get with lock. It's retrieving it off the off cache and locking the document. You can still do gets on it, but you can't do any writes. So in this case, it fails. It tries to replace it because it is locked, and then to unlock it, it either times out if you don't do anything, or that first server that generated the lock, does a storage operation with the CAS, which also generates a new CAS, and it unlocks after that's complete. I think the maximum amount of time you can lock a particular document is 30 seconds. That's the maximum time before it automatically times out. Of course, you can specify the maximum amount of time in that get with lock statement within the SDK. Expirations. So storage operations with expiration. So basically, many CMS frameworks, I know Rails, we have Rails support and other support for other frameworks, where you can simply use Couchbase for your cache, just like Memcached. You can use Memcached. Anything that supports Memcached, you can point it at Couchbase port 11.2.11, and it'll work just the same, only the performance will be slightly better because it's distributed. So in most frameworks, it's pretty simple. And for Couchbase and Rails in particular, that one I'm very familiar with. A few lines of code, and you're using it for all your Rails caching. When you want to create your own sort of TTLs on documents, you just provide the duration in seconds. Set add replace here. In Ruby, it's passing in a TTL. In Java, there's an actual parameter. The second parameter is the TTL. You can also update just the expiration only with the touch command. You can also do a get and touch, where you retrieve the document and also update the expiration. Touch merely updates the expiration, and it looks kind of like this. So here I'm adding a TTL to a particular document. Now, if that happens to expire and I do a get, we've got, as if it doesn't exist. Basically, I'm going to get return null or nil. It doesn't exist because it's been expired. However, it still will exist on disk. Just for efficiency, we don't actually delete expired documents until we do our compaction, our online compaction. So at that point, we'll delete off disk all the expired documents. So if I touch, I update the TTL. Okay, so let's talk about durability. So we can actually what's called observe and get callbacks for when documents have been written, when a document, a key value pair, a key document pair has been written to disk, or it's been replicated, or been on a replica disk. In Ruby here, you can see, in this case, the first example, right here, is I have a a key, my key value, and I have observe in this hash, and I have persisted and replicated. In this case, I want the callback to come back when it's been persisted to disk on the active partition, and when it's been replicated to another server. In Java, these are enumerations, so we want to persist to master and replicate to one node. You can also have replicate to two nodes, or replicate persist to on two disks, which is the master and a replica, for instance. And you can do all of them, or just one. So in this case down below, we have add and replace, but just tell me when it's been replicated to another machine. and the same with Java, replicate to 1. So here's a visualization of what I was just talking about. So here we're doing a storage operation with observe, persist to 1, and of course it goes to RAM cache, then the disk write queue, and then when it gets to disk, we're going to get a callback that it's done. So you can see that you can understand here that obviously it has to make it to the disk write queue and get to the top and get on disk before you get that callback. So durability requirements do add a little bit of latency, and you should use them when you need them, when they're important to have. If you do them for every operation, you're not going to get the sub-millisecond latency that we talk about, because you're going beyond the RAM cache and you just want to make sure that it's on disk. But there are times where that's very important, for particular use cases that you may have, in which case that's why we support this. Replicate to is going to generally be faster because it just has to go across a wire to another machine, and then you'll get your callback. So in this case, I'm doing storage with observe with replicate to, and once it gets to another machine, we're going to get that callback. And that tends to be faster because it just has to go across the wire. Of course, if you use the combination of persist to and replicate to together, you're going to increase the latency. And then, of course, if you want it not only on the primary active partition disk, but also on replica disk, that'll take even longer before you get that callback. But it is, very valuable for the use cases that have durability requirements. And, use them for the particular documents that have those requirements. For instance, don't use them for your session store session documents. You won't need, that's not necessary for, as an example. That completes our summary of Couchbase operations, SDK operations. And I'm going to do a sort of run-through demo of doing some operations with Couchbase. I'll do some with Ruby, and then I'll do some with Java. We actually have a developer day content I developed some time ago when we were touring around the US and Europe, training developers. And there's a number of different languages in there, and we're going to use that just for this demo, and we'll do a different demo in Couchbase 103 with modeling and show different kinds of stuff. But for fundamental SDK operations, that's a great set of files to work through in any particular language that you're going to be using, because it really demonstrates all the different operations very clearly. So here we are on Couchbase Labs/Developer Day. You can see right here, Couchbase Labs Developer Day. URL's up here, GitHub. So I'm going to clone this repository locally. As you can see, we have a number of languages in here. I'd say there's a couple that are incomplete, like JRuby and stuff, which isn't as popular as it once was. And we have Go and Node.js, PHP, Python. So this is really quite good to go through the SDK operations. Like I said, we were doing this as developer days around the country, and so let's git clone, paste that in. I actually have it. I'm just showing you, just for the sake of showing you. It's not super big, but there's a bunch of files in there. But I actually have it cloned here, and I'm in the Ruby one, and I'm going to kind of show you. So this first one, the L1 connect, is making connections to Couchbase. Here I'm making just a default connection to the default bucket using localhost. Here I'm specifying the actual bucket I want, and here I'm still using the default bucket, but I'm using the I'm passing in the URL. It's also, if you do have more than one Couchbase node in your cluster, it's a good idea to actually configure up your application with all the IP addresses of your cluster, because if a node goes down, if you have a node failure, for any reason, your Couchbase client, if it only has one URL configured, if you reboot your app server, for instance, and you've taken that particular node that you put in the put in your configuration file for your application, you put a particular node, but you actually remove that node and add another node. Now, if you reboot your app server, it won't connect to Couchbase because that IP address is gone. So it's a good idea to put as many nodes of your Couchbase cluster into your config of your application so that it'll try all of them. If the first one it tries, it can't connect to for any reason. So, you know, a lot of times people forget to add, once they've added, you know, a few nodes to their cluster, they forget to update their application. So here I'm also, this is sort of connecting to a test bucket with the SASL password. And I have to make sure I've deleted that from my application, I'm sorry, from my Couchbase so that we can see the failure there. So this is what we recommend. Here is like a node list. Of course, I only have one node, so I'm putting 2 local hosts here. But, you know, generally speaking, you should, you know, like I said, put a list of nodes rather than just a single node in case, you know, that node goes down and you remove it from the cluster and then you reboot your app machine and it doesn't have the cluster map, so it only goes to that one node which doesn't exist anymore. So let's run this one. Maybe and we've got a failure to connect to that SASL bucket. And I put a nice message here. Did I actually create the bucket with that password? So let's go to the admin UI. Let's see our buckets. Oh, I don't have a test bucket, so let's create one. Oops, probably want more than that. 30 megabytes, and let's put in a password. Let's put the right one in, which was password. No. So that bucket's coming up. There we go. So now let's run it again, and there we go. It's working. So this is basically sort of the hash output of the first connection here, and then the hash output of the second connection to just the beer sample bucket. The next one is O2, and this one is about just general storage, storing anything. Here we're storing a string. We're storing a string here. We're using the add operation, and if there's an error, if that exists, I don't expect this to exist. But it looks like I'm using the same. First, I do a set operation with the key is my test, and then I'm doing an add operation of my test, and of course that's going to fail because I already did a set. And then here's a replace operation on the same key, and then here's a replace on a new key that doesn't exist. And I'm going to get an error not found because you can't replace something that doesn't exist. So, and then finally down below, oops, I'm doing the right click. Down below, I am deleting a key. We're deleting keys here, and then here we're doing quiet mode. So we return nil on gets. For things that don't exist, and then finally we're creating with a TTL of 3 seconds, and then I do wait 4 seconds and try and do a get, and it doesn't exist, and then I do again setting my test with a TTL of 3 seconds, and then I loop and sleep for 2 seconds and continue to repeat that get. Well, in Ruby, it's get and touch is still a get, but you also pass in a new TTL. So I'm doing a get and touch for 3 seconds and then sleeping for 2 seconds in an endless loop. So let's run that. That's 2. And you can see here, let's go up. Oh, it's going to be scrolling. Here I'm doing a get. This is where I'm trying to add the same key, but it exists already. I replace it, and then I try and replace on a non-existent key, and I get a not found error because you can't replace something that doesn't exist. Adding another key value pair. Now I'm deleting them all. I create one with a TTL and I wait for 4 seconds, and when I try and get it, I get a nil class because it doesn't exist, and then forever. Sorry, that's the expirations right here. Sorry, this was a get after delete. Sorry, this is get after delete. So this one, I'm setting a TTL, sleeping for 4 seconds, and TTL is 3 seconds, and getting a nil. And then down below here, forever, I'm doing a get and touch, and resetting the TTL and sleeping for 2 seconds over and over and over and over and over. Forever. So let's kill that. Storing JSON. Very simple. In this case, I have a hash. I'm gonna, the Ruby will convert this hash automatically, and encode it into JSON, and then retrieve it back, and get a value from the hash. So simple. Ruby 3. And this is the JSON or hash I get back, which was converted from JSON. Let's modify that actually. When I do a get, let's add another get here. Let's 2 JSON 2. Let's just show the JSON too. Here I'm actually, so I added a statement to actually output the actual JSON. So it was a hash, I stored it as JSON, and I retrieved it back. In this case, I converted it. Even though the SDK converted the JSON back to a hash, I converted it back to JSON and outputted it so you could see the JSON. Very straightforward. So the rest of the files, we do retrieves, we do atomic counters, we do the non-JSON ops. Here, let's show the CAS. So CAS, I basically do, in the Ruby, we do what's called extended equals true. It'll get extended information. It'll get the value. It'll also get the CAS and get flags, which I ignore, which are used internally in the client. And then I get it twice, right? So I have value 1 and value 2. So I basically have 2 copies of the same document and the same CAS. And then with 1, I use the CAS to replace the data, and then I try to replace the data with the second one, and it fails. So, because the CAS mismatch. So that one is 07. And so here are the CAS values. So I do a get, and we've got identical CAS values here. Right. Then I replace the document with 1, and now we have a new CAS, and so it doesn't match the old CAS. And then if you try and do a replace with the old CAS, you get the CAS mismatch. So that's how you do the optimistic concurrency, and you can look at that file. Remember, all these files we also have the Java equivalent as well. So let's run this one, for instance. Just this file. Oh, yeah. So here we have a CAS, and then we update the document, and now the CAS doesn't, and then this tries to do an operation, and the CAS mismatch failure. So let's look at the source code here. Let's move this down. Yeah. So first we create a Couchbase client with the list of URIs here. Oh, well, I'm not looking at the right one. Sorry. Yeah, here we can create a Couchbase client. We're creating some user data. We're setting it with the JSON converter, user data. We made a class called user data. And then we just do these sets, and then we're going to get this CAS value out, and we're going to do a replace operation, and then we're going to try and do it with another with the old CAS, and there we go. Then you see the failure there because we tried to use the old CAS. So we do have this for every language. Just point out maybe we do have the observe. Of course, you can't if you only have one node of Couchbase on your laptop. You can't demo the replicate to. So there we go. I think that again, this is on the github.com/couchbaselabs/developer day, and you can play around with these files for all the operations. So the next webinar is going to be Couchbase 103, and we're going to talk about document modeling and some key value patterns and sort of the next step now that you sort of have a feel for the operations. And I definitely suggest playing with these operations, in a simple way, getting familiar with them, and getting familiar with JSON encoding and hashes and things like that. Playing around with that because it might be new for you if you've been doing relational for a long time. You'll have to kind of get out of that mode and think in a new way, a new paradigm, which is going to be far easier and more interesting, actually. So thank you for coming, and I hope you enjoy sort of Developer Day content. And of course, if you have any questions, you can find me on Twitter at Scalable, and justdeep@couchbase.com. I can actually pull that back up real quick. Here's that. And I look forward to seeing you in the next webinar. Thank you.